Welcome to this fifth episode of the podcast, The Pump Zone, presented by Pump Systems Academy, powered by Dynapro pumps. I mean, right now, just beneath your feet or behind the walls of your building, millions of dollars of heavy machinery could literally be slowly tearing themselves apart.
Yeah, and the crazy part is the operators usually have totally no idea, just because the water is still flowing.
Right, exactly. So today we're doing a deep dive into our engineering sources to decode centrifugal pump performance curves. Our mission here is to show you how these graphical cheat sheets basically predict actual hydraulic behavior to prevent those expensive failures.
We really have to learn them, because just seeing fluid move out of a pipe doesn't mean the machine is healthy, You really have to learn to read its vital signs.
And that starts with the core curve, right? The relationship between head or pressure on the y-axis and flow on the x-axis.
Exactly. So if you have a completely open discharge, you're getting maximum flow but minimum pressure. Conversely, if you restrict the system completely,
Which means zero flow.
right, zero flow. In that closed state, the pump hits its absolute maximum pressure. We call that the shutoff head.
I always think of this like driving. Going up a really steep hill, that's your high head, and your car slows down so you have low flow. But speeding on a flat highway, well, that's low head and high flow.
That's a really great way to visualize it.
Now, the sources mention converting pressure into meters of water column. Is that essentially calculating the exact physical incline that the pump can conquer?
Yeah, it is. Converting that abstract pressure to meters of water column lets you directly compare the physical demands of your specific piping system to the actual tangible height the pump can lift that fluid.
Okay, so we've matched our physical incline, but moving all that fluid requires power, and that brings us to the physical limits of the machine. The sources talk about efficiency, power, and NPSHr curves.
Right. So the efficiency curve shows how well the pump turns electrical power into hydraulic work. It peaks at the best efficiency point, or BEP, which minimizes vibrations.
And then the power curve is just used to size your motors, right?
Exactly. And finally, you have NPSHr, which stands for net positive suction head required. That is the minimum input pressure you need at the suction side just to keep the pump fed and prevent cavitation.
Wait, hang on. If I open the valve completely to get maximum flow, that means less resistance. So wouldn't that make it easier? Could I actually overload the motor doing that?
Well, yes, you absolutely could overload it because you're suddenly moving vastly more mass. As flow increases, pushing that massive volume of water per second requires way more physical energy.
Oh, wow. So the power requirements just spike?
They spike dramatically.
Yeah.
And at the same time, your NPSHr goes up. If the pump is moving a massive amount of water but gets starved of input pressure, the water inside literally boils at room temperature.
Wait, really? It boils just from a pressure drop?
Yeah, vapor bubbles form in the fluid. And when those bubbles hit higher pressure zones inside the pump, they violently collapse against the metal impeller.
And that's cavitation.
Exactly. That implosion will literally eat away solid chunks of metal.
So by just throwing the valve wide open, you could basically burn out your electrical motor and tear the pump apart with boiling water bubbles at the same time.
Which is exactly why operators can't just run these pumps wildly. But I mean, real-world system demands fluctuate.
Right. And you don't want to buy a new pump every time conditions change. So the sources say operators rely on families of curves by adjusting impeller diameters or motor speeds to alter performance.
Right. You shift the curve to safely hit different points. We divide these operating zones up. The BEP is your ideal spot. Then you have the POR, the preferred operating region, which is a bit wider and safe for continuous use.
And then there's the AOR, the allowable operating region. It's kind of like a dartboard, right?
Oh, dartboard. How so?
Like the BEP is the absolute bullseye. The POR is that safe inner ring. But the AOR is the outer edge where, you survive, but you're risking long-term damage if you hang out there too long.
That is a perfect analogy. Because when you operate out in the AOR to the right of the BEP, you get cavitation. And to the left of the BEP and the AOR, you get flow recirculation inside the casing,
Which creates unequal pressure.
Yeah, exactly. It puts this unbalanced force on the impeller. And that force causes the heavy metal shaft to literally deflect and bend while it spins.
Just slowly crushing the bearings and shredding the seals.
Slowly but surely. Frequent use out there causes premature wear to practically everything.
Wow. So just because the water is flowing doesn't mean the pump isn't dying. I'll leave you with this. Is your pumping system unknowingly operating out in that AOR right now, slowly destroying its bearings just because the fluid seems to be flowing fine?
It's definitely something you should investigate the next time you hear that heavy machinery humming away.
Absolutely. Thank you all for listening. Be sure to tune in to the next episode of the podcast, The Pump Zone, presented by Pump Systems Academy, powered by Dynapro Pumps.